13 minutes longer because this introduction took this 13 minutes, and obviously we have to cover the full time for it. At this moment, I am changing to share screen mode, and I bringing in my presentation, and I start my presentation. Whatever is happening on the screen from this moment onwards is not so important for me. Please just shout if I have to stop for whatever reasons. So as the title said, the presentation will focus on cyber-physical systems, and especially next generation cyber-physical system, and not with manufacturing and production in the focus, but more the social and personal utilization of the cyber-physical system. I'm very pleased that we could initiate this course with Punet, and hopefully you will find it entertaining and useful. So this is for me a first online course with India. I hope that in the end we will be all satisfied and pleased with the result. But you heard a lot of things about what I have done as a professional. But if you are interested in my presentation materials and papers and publications, I suggest you to go into the Google Scholar, and then you can see what sort of papers I have, especially what are those topics which I am dealing with in the last couple of years. If you want to get further information about me, then you can go into the ResearchGate as well. And in the ResearchGate, you will be able to see that what sort of discussions I am in, what sort of questions are interesting for me, and what sort of answers I provided. This is also a very useful information source for you, I believe. So let me start with an African proverb, what you might know. A wise man never knows all, only a fool knows everything. And this applies to me. I know my limits. I know that I have limits in a special field, and for this reason, I believe that I will attached to those sort of things what I really practiced in the couple of years, in the last couple of years, and what I have some experience in. We built up the course according to a massively online course principle, and it means that every course, every lecture is divided into two parts, block 1 and block 2. The first block here is introduction and objectives of the online course, and this is what I would like to present it. And first of all, about the pedagogical approach and justification of the course. Obviously, every one of us knows that human learning actually has two main streams. One of the formal learning, and another one is the non-formal learning. The formal learning is the institutionalized learning, various forms like instructional learning, constructive learning, and explorative learning. On the non-formal learning side, intuitive learning, search-based learning, professional learning, and very recently, autonomous learning came into the scene. Why is it important is that actually here the major effort is to have a kind of blended learning in which all the three approaches will be blended, while the other side is the lifelong learning, which would be supported by the autonomous learning. So autonomous learning is known almost 25 years. It is a kind of new old paradigms to learning. And it is initiated by that sort of observation that in the modern society, we never stop learning. And it is important, especially in the innovation society and economy, where the new technological development, the new social development should be monitored.
Professor
So
Tandon.
autonomous learning is a new pedagogical concept that supports lifelong learning, and it is a kind of self-directed learning with minimal or no aid of instructors. It is fully autonomous, but I have to make a comment on it. So, in order to be proficient in autonomous learning, first we have to know how to learn, and obviously many more technical things. So if we consider autonomous learning as a kind of pedagogical approach, then we can identify two different approaches. One is the transitional approach. This is what we practice here.
Let him continue.
Autonomous learning. The idea here is that before the students are going into completely autonomous learning, a kind of conceptual framework is provided for them. This course is about that, to provide the conceptual framework for all the students who want to learn. Because obviously this completely autonomous learning will support everybody's lifelong learning. It means that not only just the university during the university years, but afterward. And what is important here, that actually a kind of meta learning should be somehow implemented. So on the way towards autonomous learning, we have to first of all see the challenges. One of the challenges is that the learning should take full responsibility over their goals, their way of learning, and the approach of learning. It has to be assumed, obviously, that they are motivated and responsible. It is also assumed that the learners may take advice from more experienced professionals and even seek professional guidance. So what is interesting here, that this autonomous learning based on the practicality, it is not really practiced in the field of industrial design. So our course is a kind of experiment also in that what we can achieve with it and what we can use for it. So the main issue is here to develop the learning autonomy of the students. And obviously, different modes of learning can be applied by the students. This is mainly a attitudinal issue, but the major issue is what I mentioned here, to challenge the students, to take them out from the comfort zone. What it exactly means is the following. That everybody feel safe and comfortable in the so-called comfort zone. But when we go further and we go to the so-called fear zone, the personal view is affected by other views, and also a kind of lack of self-confidence, in a sense that, do I know everything? And then of course we tend to find excuses why we are not knowing. But then if we go further, then comes the so-called learning zone. And in the learning zone happens, for instance, that we pick up new challenges and acquiring also new competences. And then this way we extend the original comfort zone. And then we go into the so-called growth zone. And then what the most important thing is that, having already a kind of self-confidence in automated learning, autonomous learning, we set up new objectives and new goals, and actually we can realize, in a sense, our dreams, and also find new purposes. And obviously this leads to the real life application, the so-called productivity zone, where we can have a benefit of all these things. So let me summarize briefly the tenets, or the philosophical tenets of this new learning. The learners, if the learners are not going after what they want to learn, they never have it. If the learning do not ask, the answer will not be provided. If the learning do not explore, the knowledge will always remain what is already possessed by them. And if they don't make step forwards, they will remain in the same place. These have obviously a lot of influence on how to organize autonomous learning, how to plan, and what became a kind of general model, and this is what we used at the development of the course, that first we have to identify the needs, then we have to set the goals, then we have to plan the learning procedure, then we have to select the learning resources, then select the learning strategies, then practical executions are needed, and monitoring the progress, and finally, reflection on the results. So understanding the purpose, accepting the responsibility, sharing actions and resources, taking part in planning and doing, and reviewing state of progress and generalization of the experience are main elements here in addition to the circular planning. So something about the development of the learning autonomy. Obviously, it is based on the ability of the students to identify a learning goal. Several students with different background, with different knowledge levels joined the course. Actually, we tried to collect information about what their background, what their current knowledge, and what their intentions are, but we couldn't really identify their learning goals, why they are approaching this presentation, in addition to obviously the fundamental one. They want to learn more about the future of next generation cyber-physical systems. But we put together the course content in a way based on which different actions and efforts can be made to achieve the goals. And we offer the opportunity to consult with us or even other experts. You will see that I will several times refer to certain publications, and these can be also used by the students as auxiliary sources of knowledge. But the students are supposed to achieve a kind of self-efficiency over this course, but especially after the course, when they use this conceptual framework what is provided here in the course and select certain topics in which they want to deepen and want to familiarize themselves better. So they have to have this ability to find their goals, further goals. And obviously, we assume that during the course, competencies like the attitude to learning in this way, the capabilities of learning this way, the knowledge, the skills, and the experiences will be growing. One of the experts is David Noonan in the field of autonomous learning, and I would like to show very briefly this table. And this particular table says the levels or talks about the achievable levels of autonomous learning. So first, there must be a kind of awareness built, and it means familiarization with the learning objective and learning contents. Then a kind of involvement, a kind of interiorization should be achieved, and it means that choosing the best matching text to knowledge domain, to the knowledge domain, the targeted knowledge domain. Then a kind of intervention has to be practiced, selecting alternative approaches according to personal interest. Then a kind of creative phase comes, making initiatives to create own learning objectives, and then in the perfection stage, connect the virtual classroom and the world beyond, and to see what really needs to be learned there. If comes to the benefits of the autonomous learning, we can say that it offers, first of all, a methodological basis for lifelong learning, and it enhances the learner's curiosity and motivation. It's according to our past experiences, also with the MOC courses, it increases the effectiveness in and the tailoredness of the learning. Opportunities for proficiency will be also provided and caters for the individual needs of the learners on all levels. And actually, contrary to the fact that it is online course, it allows some sort of socialization, partnering, and teaming up with peers and other experts. There are disadvantages that I would like to mention that contrary to everything, there is a social isolation and the virtualization related to autonomous learning. But actually, we have to consider the fact that when you, in your life, try to practice autonomous learning, then the social isolation is almost always with you because you learn from yourself. And then obviously it has been already found in the literature that the disadvantage of autonomous learning is that it may not fit equally well to each individual. There are people who like it, there are people who less like it. But it is important to see how to take the most of it. First of all, it has a culture, which means that when you receive this sort of I'm mentioning it to all students that when they receive this sort of conceptual framework, the best is they start immediately thinking about that what they want to further study, what they want to specialize, and how they want to achieve this sort of goals. And then obviously the responsibility speaks itself. If the students are not committed to learning more than is presented in this conceptual framework, then none of the educators, the teachers can force them to do so. So it is their responsibility. And for this reason, what is suggested that don't hide in the crowd. If you have a problem during these hours of assistance, ask the question, let's try to clarify it and make clear everything which was not obvious or was even incorrect. And since there will be discussions and Q&As, take active part in these discussions and the question and answer sessions whenever they take place. And obviously, it is very dynamic. The content what I will present is extremely dynamic for the reason because the technologies and the technology utilizations are dynamically changing. And I ask from every student to understand that maybe even the very last developments are not included or couldn't be included just for the reason because actually they are not yet in the overall practice of cyber-physical system engineering. On the other hand, I believe that I will come out during this lecture hours with many novelties, a kind of mind-twisting novelties, what everybody can think about. And obviously, the knowledge utilization and building up skills also continues in the practical. So let us work towards a great success. So this will be a novel assisted autonomous online course that intends to provide a glimpse on the near future of domain or system engineering, more specifically on the next generation of cyber-physical systems. And I hope that you will find it useful and enjoy it. And but I kindly ask you commit yourself to learning and cooperation as much as is possible. We need each other. The presenters and the students need each other in the course, and I would like to show this relationship with the famous drawing of Escher's, when actually the creator and the user are together and they work together in a harmony. So I promise to mention some suggested literature, Nuna's publication towards autonomous learning with the principle in language learning is one of them, what I suggest. Then this teleconference in support of autonomous learning, a very meaningful learning, and then human agency as a self-cognition of human autonomous learning. And the next one is autonomous learning, intelligent vehicles, engineering. These are the four things which I suggest. Now I stop with sharing with the presentation, and I would like to come back to a discussion because we have a couple of minutes for a discussion. So do you have, please, any comments on it?
Are you able to hear?
Here, no sound.
You're not able to hear. Actually, I was telling you something in the beginning.
Yes.
But it's okay. Now, actually, Professor Kondekar wanted to speak something actually before you start. But anyway, now he has left, so you can continue. You may continue.
Okay.
Thank you.
But what I would like to kindly ask you that do you have any comments, please?
So it's okay from my side. If any participant has any comment, please say so. Otherwise, you can continue, and we'll once you finish your lecture one, we'll ask the participant to comment anything if they want to comment.
Okay. So if I don't know, I heard something, but I don't know if it was the same. Seemingly not. Okay, then let me change to the second block, if you agree on it, please, and then let me start with the second block, which is about the overview of the content of the course. And first of all, you heard a couple of words already about the intention of the course, and to the question that what it is all about, the title explains everything. Designing, so this course try to support designing cyber physical systems. I also mentioned that we are not talking about the past stage of cyber physical systems. We are looking into the future, and we mainly focus on smart cyber physical system. This is the current core issue. And we are not proposing the cyber physical systems in this course for exclusive manufacturing and production application, but mainly for societal and personal utilization. Of course, it is not excluded that those sort of principles, what we discuss here, can be imported and used in the field of manufacturing and also production. But the cyber physical system domain, an extremely heterogeneous disciplinary domain, and the methodology of, for instance, how to do research here and how to develop systems, it's not yet completely settled. Cyber physical systems are complex, multi-level. And for this reason, their designing needs also a complex activity, a multi-level activity, and a collective activity, which goes through a 5-stage process. The first one is the conceptualization of cyber physical systems, which converts the needs to the ideas. Then the functional design comes, which converts the requirements to certain functionalities. Then the structural design comes, often called architecting, which considers the transformation of the function-based operation to components. And then the computational design is coming, which establishes process flows with compositions of algorithms, which will be called mechanism, computational mechanism in this case. And the fifth one is the so-called implementation and design, which is about the handling of the algorithms for the cyber-physical systems and also for the data management, in addition, obviously, to the physical devices which are included. So we need a new view and attitude to be optimal in cyber-physical system design. So now let me introduce the course content, what is specifically offered here. We are now in the introductory lecture, which is focusing on the pedagogical approach, and it was preceded by an entry quiz. Not everybody submitted the quiz, but it can be still later on. We will have 2 weeks, actually 5 days for the presentation. This week is focusing on the understanding of cyber-physical systems and gaining insight in cyber-physical systems. The second part next week will be more about the engineering of cyber-physical systems and the support of designing cyber-physical systems. If we look into the concrete context, then today we are already having this lecture of introduction and objectives of the online course. And the second lecture after the break will be about the characteristics of cyber-physical systems. So this module, these 2 lectures together with the practicum, is focusing on the objectives and the characteristics. Tomorrow, there will be 2 more lectures. One of them, the typical functionalities and enabling technologies of cyber-physical systems, and a lecture after the break on the generations of cyber-physical system functionalities and generations. This is the main topic also for the practice. Then the engineering exam and examples of cyber-physical systems will be provided on Wednesday. First, I will deal with the very novel issue of cognitive engineering of cyber-physical systems, and then I will show at least 2 prototype cyber-physical systems which were developed here in PhD projects with my former PhD students. You will see that we are really going to the domain of smart cyber-physical systems with this. Then Thursday, our topic will be system control and supervision, because obviously the system control issue for traditional production systems is a well-known field of knowledge. But if we are talking about smart systems, adaptive systems, or even evolving systems, the system control gets a completely different shape. And obviously, the supervision by human is also a issue there, as the automation level of this system is growing. That will be discussed on Thursday. And then also the sensing and actuator technologies will be discussed from the perspective of the next generation cyber-physical systems. And Friday, we will talk about the massive data management issues within the cyber-physical system concept. And there will be hopefully you will see it also interesting presentation on context management, because if cyber-physical system, smart cyber-physical system should make decisions, then decisions should be made with respect to the context. So massive data and context will be the topic for Friday. Next week, Monday, in Module 6, we will deal with the computational mechanisms. And the first lecture, the 11th lecture, will talk about the probabilistic and evolutionary mechanisms that can be used for smart cyber-physical systems. And then we look into the topics of machine learning and training. And here, what I would like to convince you about that the traditional learning techniques and reasoning techniques can be as useful for next generation cyber physical system than the current hype, for instance, deep learning or other forms of automated learning mechanisms. Then next week, Tuesday, we will talking about the machine learning. And first, we discuss the canonical, so-called canonical problems of machine learning. And then we look into the fundamentals of the connectionist and neural mechanisms of machine learning. Then we will go further to the convolutional machine learning, and we will discuss the role of agent technologies and various types of agents in smart cyber physical systems. Next week, Thursday, model and component-based development of cyber physical system will be at stake. And after designing for adaptation and also system evolution, which are new topics, actually not really heavily discussed in published books. Then the module 10 will talk about the interaction and dependence on cyber-physical system. First of all, the new principle of understanding and practicing interaction with cyber-physical systems will be presented, and then the last lecture will be about the concept and the implementation and use of digital twins in cyber-physical context. So this is what is this sort of conceptual framework means. And as you can see, it is 20 presentation altogether. Every presentation is divided into 2 blocks. So what it means is actually that, that you will be confronted with 40 topics which are all relevant for the cyber physical system development. At the same time, I have to tell you that there are topics which I had to leave out because nothing else, nothing more can be included here. For instance, what is rapidly developing using ontologies and capturing cyber physical and managing cyber physical system knowledge between system of systems. These topics I had to leave out. Maybe in the next course we can talk about it. Something about the didactic elements of the course. So there will be 20 lecture hours for the theoretical fundamentals, complemented with 10 practicum hours. So actually what is expected that during this course, you will spend something like 30 hours on self-study in order to familiarize yourself with the topics presented. And obviously there will be exam quiz after finishing the course. And with this, we would like to measure how you acquired a kind of framework knowledge and how much you familiarize yourself with the basic content. So the total course duration is what, according to our plans, is 33 hours. And I don't know if you have credits for this type of course. In Delft, this was a 3-credit course as such. So what is the view on you, on the attendees on this course setup? We think about you as chief technological officers for cyber physical systems. Let's assume that you will work for a company, and this company wants to specialize itself in developing next generation cyber physical systems for non-heavily industrial but social and personal applications. And here is your role, the chief technological officer, because what you have to practice there, a kind of holistic view to know if the cyber physical system is such a complex, heterogeneous domain, then what is that holistic knowledge, what brings the pieces, the different domains together? So actually, this holistic knowledge is what the course try to provide you. Not specialization, but holistic knowledge. And obviously, we are trying to enforce a kind of superdisciplinary view. The essence of these are that you, as a chief technological cyber physical system officer, you have to be aware of the societal and business needs and demands. But you also have to be aware of the technological developments and the technological affordances. And from these, or having the knowledge on these two fields, then you have to be able to develop a comprehensive strategy for the company. How to develop next generation cyber physical systems and how to be competitive on the market, how to fulfill social demands, and how to make the best exploitation of the technological affordances. It will be interesting for you as a person like this, how to work, because obviously you will be working with a kind of agile, which means problem-driven, purpose-driven composition of specialized heterogeneous developers teams. Maybe very large number of them, for instance, system architect people to, let's say, physical component developers, and then system simulators and analyzers, and so on and so on. And what is also there, that obviously every domain or every specialized team has their own knowledge domains. And what is interesting, that these knowledge domains not only separate typically and even not in overlap, but they reflect different cultures, different solutions to problem solving. So actually, you in this chief technology officer position should be able to oversee the domains of knowledge which are relevant and which are delivered, conveyed into the development strategy by the different teams. And then you have to be able to make decisions and to develop collaboration with those teams which are implementing that particular strategy of the company. So it means that actually you have to practice a kind of system integrator role. This is what you have to achieve. And then the designer, as a negotiating integrator, first of all, should be able to collaborate. Because as I wrote here, even the most simple cyber physical system needs disciplinary collaboration. Otherwise, they cannot be implemented. It cannot be developed and implemented by one people or even a very few number of people. It is necessary to involve system specialists, hardware specialists, software specialists, knowledge specialists, cognitive experts, and even social specialists in the development of the next generation cyber physical system. So important also that for the negotiation, you need to develop transdisciplinary team and you need to work together with their members effectively. So you have to learn their language and you have to be able to communicate with them. And however, there is an obstacle here, as I mentioned, that the teams working in different domains and having different sets of knowledge also have different mental models. So they are following different reasoning strategies. They have different engineering strategies. They use different support tools, computer-based, computer-aided tools. And also their creative culture can be different. Some of them are more hierarchical, some of them are really working bottom-up. So the CPS integrator cannot be a specialist of all, but it should be a person who has the capability to form a holistic view. And in this holistic view should have the capability to initiate new concepts, new ideas, and also direct the negotiations towards the implementation. So it is a new role. It is not the conventional roles which are practiced in the industry at this very moment. And this is why I believe that the universities should be able to prepare the students for the future challenges. And in this particular course, we try to provide this conceptual framework which is needed for the students to act as a kind of negotiating integrator, as a designer who is not specifically designing everything on his or her own, but communicates with people and consolidates ideas and consolidate process flows. So this was about the course content and how we see the attendees of the course. Then obviously there is one more attendee of the course, and those are the systems. Because cyber-physical system is one type of system. And I would like to continue the presentation now with a kind of overview of the system, the major ideas related to systems. And obviously, it is known by all of you that everything is complexified and everything is becoming a system. And completely new types of systems emerge. I personally believe that next generation smart and intellectualized cyber-physical systems are one representative of this. But although I use the word that emerge, that these systems are emerged, they are not emerging. Their concepts may emerge and the opportunities for this type of systems may emerge, but actually they should be designed very carefully and in a dependable way. So as I mentioned to you, that the systems are becoming more and more important, and for this reason the future industrial design engineers should focus on systems and not only on design, products and services and many more things. For instance, they have to be aware that we are not working just in the product society anymore, not in the goods society anymore, but we are moving towards the so-called experience society. And later on, I will elaborate on this issue in more detail. So we believe that cyber-physical systems are representing one important family of engineered systems, which actually will have much stronger influence in the future than they play at this very moment. And the simple reason is that because a lot of traditions are present at this very moment in the cyber-physical system knowledge arena, but a lot of things are somewhat blocking the further development and out-of-box thinking. So we believe that the next generation cyber-physical systems will be multi-actor systems, and they will deeply penetrate into real-life processes. The example of this penetration into real-life processes are already there in let's say, in production or in manufacturing. But I will show you that actually there are many more real-life processes in which we can penetrate very deeply, and we can have useful things there. And obviously, further clarifications will come soon on this. So we are talking about systems now, and we said that there is a plurality of systems. If we would like to characterize engineering systems based on their characteristics, then we can talk about physical systems, virtual systems, observable systems, non-observable systems, intelligent systems, or purely mechanistic systems. We can talk about abstract systems, and we can talk about concrete systems, and so on and so on. So a extremely huge number of characteristics are there, what we as designers should consider as developing systems. I cannot explain all these things, but most probably the words which I used here are talking for themselves and self-explanatory. But there is also one thing what we have to clearly see, that not only the characteristics of the engineered systems are increasing enormously, but also their paradigms, the model based on which they are built up is also radically changing. Because in the past, actually in this field, we had the so-called advanced mechatronic systems. And many of them was using also so-called embedded systems. But these embedded systems obviously was just a kind of stage in the development. Later on, distributed real-time systems appear. Just consider the control of the brake of braking in your car. It is definitely a distributed real-time system. And then network agent-based systems were introduced. Agents which are based on, for instance, camera images, and they record when you are over speaking and send you a ticket. And this is also something what belongs to the network, so-called network agent-based systems. And then the Internet of Things, which was also a kind of paradigmatic contribution and shifted the paradigm. And then we arrive at the paradigm of the cyber-physical systems, and many refer to it as a first comprehensive, fully fledged implementation as the Mars rover. Yes, this was a kind of breakthrough innovation in this particular paradigm. But most important thing is that we have to be aware that these paradigms, the conceptualization frameworks for the engineering systems is rapidly changing. And when I'm talking about cyber-physical systems as the last one, I tell you that I could have put one more here, but I didn't want to make it more complete and more challenging for you, because cybernetic systems are already on the horizon, because the socialized cyber-physical cognitive systems are pointing into this direction. So most probably in a couple of years, we have to put one more balloon here and indicate cybernetic systems. So let me place the concept of cyber-physical systems on the landscape of systems. We have two types of systems, natural systems and artificial systems. Artificial systems are what we call the engineered systems. Natural systems can be physical, can be biological, or social. Artificial systems can also be social, but they can be also mental systems and can be engineered systems. If we go further with the engineered system, the decomposition of the engineered systems, we can identify linear systems and we can identify non-linear systems. Most of the traditional engineering systems belong to the linear systems. For instance, the ordinary and the complicated technical systems belonging to this category. However, most of the complex next generation cyber physical systems will be non-linear. Just consider the fact that they will be able to adopt themselves. They will be able to evolve. And these are the reasons of the non-linearity. And they will be somewhat resembling to the traditional regulatory system. There will be adaptive system, there will be evolving system, and even self-replicating system. Not the traditional way, but knowing the objective, creating something which is able to solve the problem. So this is what we are talking about. And I mentioned to you that the next paradigm will be most probably cybernetic systems, physical, cyber, social, mental. And most probably most of you heard about, for instance, implants and extending the human nervous system with artificial limbs or whatever. These are what we can call cybernetic systems. A very strong, very intricate integration with the human cognitive system, with the human nervous systems, and so on and so on. But this is the next generation. For the time being, we don't go so far as cybernetic system because we have a lot of things here in the smart intellectualized cyber physical system domain. Hope my explanation about this sort of landscape was clear and clarifying what we are talking about. I told you earlier that there are changes also in the industrial business because the traditional products, the traditional services are changing their characters. And nowadays, we are talking about offerings rather than just talking about products or services or whatever. So let's see what is the trend, is the offering. So if we create a kind of diagram, let's say starting from the 1950s, when the commercialized products after the Second World War were dominating, and many previously industrial equipment went into the daily home usage, consider coffee maker, fridge, and whatever, and up to our present time. And if we actually consider the societal demands, what the people needed, and what sort of technological affordances were there. Please recall, this is what I said, that a cyber-physical system integrator and chief technological officer should be also should be aware. So here it is also playing an important role. And then what was the first step starting in the 15s, that we had so-called artifactual product and a kind of process-oriented design and engineering practices. Then, somewhere halfway through after the 80s to the 90s, actually the system thinking, the dedicated system thinking came to the scene, and the valuable product services appeared. So the products were extended towards services. But we are going further, and We are in the stage now, we are in the second decade, in the second millennium, where we are talking about adaptive environments. Cyber-physical systems are very important to contribute to this adaptive environment. But what is interesting here, that actually these adaptive environments provide tailored experiences tailored to the stakeholders. So this is what we can identify here. There is a shift in the paradigm of the artifacts as well. Products goes to systems and environment, and at the same time, the offerings also change because it is not just exploitable processes, not just services, but also experiences are offered to you. Please don't forget this figure because we will revisit it later on when we will talk about the interaction with cyber-physical systems and the experiences which are provided by cyber-physical systems. So we are talking about experiences, and obviously experiences can be assets. You can sell it as you can sell oil or a product or whatever. So experience can be sold, and when they are sold, we can talk about the experience economy. Service is known, I believe, because it is already a 20 years existing concept. But the majority of the services at this time or in our time are becoming more and more intangible. So they move to a kind of experience domain. We claim, and I enforce this statement, that experiences are distinct economic offering. So in the future, we have to think of experiences because they are different. And they are different as, for instance, from goods and traditional products are different from services. We have to understand the domain of experiences or experiences. At this very moment, it is not fully exhausted. There is a heavy research effort and practical effort there, but I dare to tell you that many opportunities are not seen or unexplored yet. And the problem is that experience is not necessarily related to one particular physical artifact or producer. It is much more complex. It is much more intangible. And this is the one of the challenge in dealing with. And obviously, experiences are inherently personal. My experience with the same can be completely different than your one. It depends on your attitude, what your expectations are, and ultimately your desires and mindset. So if we summarize what we were talking about until now, so the commodities, goods, services, experiences are in the scene. The future is so-called makeovers, which popped up but not completely elaborated the topic here. So what we have to know that experiences emerge as a next step in progression and providing economic value for the society and the individual people. Cyber-physical systems can significantly contribute to this experience, but obviously this experience is, if it is connected to the individuals, the cognitive, social, and whatever expectations of the individuals, then this experience is more related to the cyber-physical systems, in particular sport cyber-physical systems, which are developed for experience applications, well, sorry, for societal and human applications. System complexity, I mentioned, systems may become physically complex and functionally complex. And they can also be psychologically complex. The interpretation is there. And if we consider the complexity and the experience economy, then we can definitely see a kind of mutual relationship between the various forms of the economic offering and the experiences there. It needs further study, obviously. There are certain quality measures to achieve experience engineering, for instance, the intelligibility, transparency, observability, controllability, obtrusiveness, perceptibility, feedback, and feed-forward thinking. And I believe this is how far I could get with this presentation. I would like to go to that slide, which is about the, sorry, I just have to find the slide, which is about the literature. So in order to further study these issues, what I was talking about, please study, for instance, lack of paper on the evolution of systems, or Friedman's systems theory gives a lot of information about systems. Also, Pine and Gilmore paper are welcome to the experience economy. And then the definition of the system thinking, design thinking from Brown, and engineering of experience for Sanders. And I also wrote a paper about the relationship between smart design and smart systems. Thank you so much. This concludes this part of the presentation. And again, I would like to connect back to you.
Hello. Thank you, Professor Imre, for a very wonderful
Sorry. Hello.
Am I audible to you, Professor Imre? Imre, you have to put on the headphones actually.
Professor Tandon, what shall we do now?
Am I audible to you? Hello, am I audible?
Yes, I can hear you now.
So actually, whenever you are delivering a lecture, also please put on your headphones, because otherwise we are not audible to you. If any participant speaks anything, so
yeah. Sure. I will do that. Thank you for that. So, I don't know why the noise, why the voice communication was so noisy on my laptop. But with this headset, I can hear everything much better.
There is some internet troubles over here also, I think so. So that's why it is causing some problem. Anyway, since we had planned to finish this lecture by 3 p.m. and have a break from 3 to 3:15, but we already, so probably we can cut down on the break and start. You tell me in what time you will be comfortable to start your next lecture.
Okay. I believe that today we will be able to discuss one more block. And one more block,
yeah,
in the second lecture, and then we can continue tomorrow morning. Then we can go further. The introductory part was a little bit longer today than planned on my side as well.
So I just wanted to check with you in how much time will you be able to start? Maybe in 10 minutes time. Shall we start?
In 5 minutes, I believe.
Okay, so we'll start at according to Indian time at 3:22. So you can have a break of 5 minutes. Don't
Yes,
come
please.
off. Let your IDs be logged in, but be back by within 5 minutes. Is it
Yes,
okay?
please.
Am I audible to all of you? All the participants, am I audible?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Just we'll start the next lecture in 5 minutes.
Okay, sir.
Thank you so much, Dan. Thank you.
If participants' videos are on, we can take a snapshot.
Your voice is not coming clear, Vijay. Say again.
If participants' video is on, but in the video is off, so we have to take a snapshot basically.
Vijay, your voice is not at all clear. Nothing is, can't make it out what you're speaking. So do you want to say that if participants have any question they can ask?
That is there, and then am I audible now?
Yeah, it's much better. Yeah.
Okay, so we can take a screenshot of all the
Fine.
participants.
So if all of you can just switch on your camera, please. All of you, please switch on your cameras.
Very nice to see you present. Actually, I like it much better, because it is not just talking against the wall, just talking about people. But this is also what I believe that if we could have a local meeting, everything would be much
All of you,
better.
please switch on your camera.
Sorry?
Yeah, if you could physically come, then it would have been more better actually.
Start with Nitya Ranjan Sahu, Rahul, Shoilam, Ashish, Sunil. Can you please switch on your cameras for once, and then probably you can close it. Let's take just one photograph.
Okay.
Okay, you can close it now, and we'll start in another 2 minutes.
Yes, I come back.
You करना है क्या?
I don't know if in this break, in 1 or 2 minutes, since I see many students, would you be so nice to tell me, just in a couple of words, if what I tried to present was new to you? Was it interesting to you? I don't know if any students could comment on it. No one is responding. Most probably everything was
Yes, sir. Yes,
known.
sir. Yes, sir. The course content is very interesting, sir. It is very useful as many of us are using the system, cyber physical system. It is really useful for us. Thank you, sir.
Thank you.
You check it out.
I'm ready for the second part, and let's go through one more block, if you agree, please.
Yes, Professor.
I go back to sharing my screen. I don't know. No, it was not shared in the last time. So the next block is about the distinguishing paradigm of or distinguishing paradigmatic features of cyber physical systems. And let me change to presentation mode. Can you see this front page, please?
Yes, Professor.
Excellent. Then I go into. So when we talk about cyber physical systems, it is a somewhat tricky and somewhat confusing business for the reason because everybody sees it differently. So this is the cyber physical system, this is the smart cyber physical systems, and someone who is coming from here, he says, or she says, yes, this is what it is. This is what CPS is. Other people coming from a different direction, they are saying, no, I'm talking about smart cyber physical systems. And they just mention cyber physical system. And they claim, no, this is what it is. So this trick is out there in the interpretation of cyber physical systems. And I have to tell you that this concept of cyber physical system exists for some 12, 13 years. It popped up in the United States. In Europe, we were talking about complex adaptive systems. And then obviously when the Americans invented the term or coined the term cyber physical system, it's rapidly penetrated into Europe. And the most dominant thing was the influence coming from the embedded computer system fields. And just to cast light on the differences between embedded computing and cyber physical system, let me give you a very brief overview that what we are talking about. So embedded systems are combined hardware and software designers that include digital processors, but are typically not for general purpose and not general purpose computers. This typical example is, for instance, the control unit in a washing machine. Embedded systems are application specific and optimize their operation and design by taking advantage of the characteristics of the application. This is somewhat true for cyber-physical system as well, but the cyber-physical system may have a broader field of application in sense. Embedded computing systems are typically pre-programmed for certain tasks, and they are often developed for real-time requirements, and this is not always possible for complex distributed cyber-physical systems. But what I claim is that cyber-physical systems are not built on top of embedded computer systems anymore. Maybe the first versions were developed based on the concept of embedded systems, but nowadays completely different principles are defining and determining the development of cyber-physical systems. So therefore, we need a different system science interpretation. And the whole cyber-physical systems as a discipline is information. I am aware of more than 300 books, which one way or other are related to the cyber-physical system theory, the concept, the methodology, application, security, and so on and so on. So it is a rapidly proliferating thing. Especially it's received an impetus by putting the cyber-physical system concept into the framework of the fourth industrial revolution, where it is conceptualized as an enabler. So we are aware of the first three industrial revolutions, which actually were taking place before the Second World War. But after that, since the mid-80s, we have the fourth industrial revolution. And the essence of the fourth industrial revolution, that it proliferates information and computing in everyday creative and executive processes. But obviously, the time axis points further, and we are already seeing the fifth industrial revolution. It started with the revival of the artificial intelligence research some 10 years ago. And the fifth industrial revolution means the revolution of intelligence that permeates the society with smart, cognizant, and even intelligent system, whatever the latest term means. So it is rapidly changing. What I wanted to show you with this figure, that we are talking about different type of cyber-physical system when we put them into the context of the fourth industrial revolution. And then when we put them into the fifth industrial revolution. The major difference is that these systems will be intellectualized and do much more intelligent things than these ones. Obviously, with this sort of making the systems more intelligent, their complexity is also increases. So Industry 4.0 tend to be achieved by the digital transformation. And this digital transformation needs certain kind of main ingredients. There are 6 major ingredients identified in the literature for the implementation of Industry 4.0. For instance, vertical integration of the processes and horizontal integration of the knowledge domains. Then application of new business models, I was talking about the experience-oriented models are there, and individualization of the offering, which is related to that. And then fusion of hardware, software, and cyberware. Later on, I will talk about the bang revolution, and this is a very concrete example for that. And also we need novel setup and control of value chain. This, if we have all these ingredients, then we can talk about the implementation, the organization and implementation of Industry 4.0. But it is not enough, because we also need concrete enablers. And this is where cyber-physical systems are coming into the scene, because one of the enablers of the Industry 4.0 concept is the real-time data and knowledge acquisition and integration. Involvement of self-adaptive systems, cyber-physical systems. And then obviously the next thing is the connection of people, artifacts, systems and services. And the fourth one is exploitation of artificial intelligence. Whatever way this contributes to the intellectualization of the system. So this is how we see the implementation of Industry 4.0, having the concept of the fifth industrial revolution already in the mind. But we also can say that if it is implemented with these ingredients and with these primary enablers, then the Industry 4.0 will be a kind of decentralized decision-making organization, which is capable for runtime self-adaptation and managing proactive processes, and provides an overall flexibility. There is a split opinion on the discipline of cyber-physical system, because many people believe that for the fact that it is amalgamating so many different domains, this is actually an interdisciplinary field. Other people believe that it is multidisciplinary, so the knowledge and the research and the engineering methods of multiple disciplines should be brought together. Many people think about a kind of transdisciplinary knowledge in which the domains of the boundaries of the included domains are blurred or even disappearing, and there will be a new science information. I believe that the next generation cyber-physical systems and the coming 10, 15 years will go into this direction. Multidisciplinary collaboration will not be enough. So now let's go back to the roots and let's see the cyber-physical systems traditional definition, and let's apply a kind of critique on that. The first official definition of cyber-physical systems came from the National Science Foundation, who provided this particular definition, namely that in a cyber-physical system, a physical mechanism is controlled or monitored by computer-based algorithms. The physical and social components are deeply intertwined, able to operate on different spatial and temporal scales, exhibit multiple and distinct behavioral modalities, and interact with each other in ways that change with context. This is a very appropriate definition, but please don't forget that it is practically something like 15 years ago. And this was useful to describe traditional cyber-physical system, like this air control system, this sort of battlefield attack system, these sort of logistic transportation systems, or for instance, a energy power system. This definition sufficiently well describes this sort of application. But obviously, we should look further, because why this initial definition and many more say that cyber-physical systems are software integrated systems which connects the physical world and the material flows and the energy flows with the cyber world, where there are information flows and thinking processes, by creating a synthetic so-called computational world. And using digital computing, they connect the physical substances and processes with the cyber substances and processes. And this is how it is interpreted as a kind of integration through software. But it is not enough, because actually we have to consider that cyber physical systems are both data and software integrated systems. Later on, we'll talk about this sort of penetration into real life processes, and you will see that this is related to their penetration into real life processes. But if we see it historically, initially we had the dominantly hardware system, for instance, bridge structures, port drives, or locomotives. We had dominantly cyberware systems like image repositories, data warehouses, knowledge bases. Or we had software, dominantly software systems and CAD packages, like CAD packages, office automation tools, AI shells. And what is interesting that this data and software-based integration tries to bring all of these together. So we can say and we claim that cyber-physical systems, as well as cyber-physical system of systems, are not only software, but also data-integrated systems, and massive data processing plays an important role in that. And we also say that this way they establish a tight coupling not only between the physical and the cyber domain, but also the computational, the cognitive, and the social realms as well. And later on, you will see that they really do many other things. Most probably, many of you are aware of the cyber physical system ontology developed by the National Institute of Standards and Technology in the United States. This ontology intended to capture the generic features of the cyber physical system paradigms. And they defined certain root terms. You can see them here, not visible, therefore I listed here, like the boundaries, if it is open or closed, the business, the purpose, the composition, the data management, the framework, the functionality, the human aspect, the life cycle aspect, the timing, real time or non-real time, and the trustworthiness. So these are those sort of major terms in which the world was thinking for a long time. Because, for instance, the functional aspect was used for talking about sensing, control, operation, criticality, business, the strategies, model, services, sustainability, the human aspects about the different roles, interaction, responsibilities, knowledge, transformation, security, safety, reliability, resilience, timing, scheduling, frequency, time stamping, and so on and so on. So actually, you can see these fundamental terms back in the papers talking about cyber physical system. So we can say that this ontology actually was very useful and very necessary at that time when it was launched. But obviously, as everything, it is becoming a little bit obsolete, because a couple of years ago, a good couple of years ago, we proposed a new definition of cyber physical systems, which are not so much into the past, but into the future. And the new elements of these definitions are that we consider the constituents of cyber physical systems as functioning network actor nodes. And they rely on data and patterns driven by cyber physical computing. It will be discussed later on. And every cyber physical system realizes a a sensing, reasoning, learning, and adaptation loop. They manifest as synergic system of systems. So this is being the system of system is more typical for a cyber-physical system than being a single actor. And obviously, every cyber-physical system is supposed to provide tailored services and avail resources in a dynamic manner, dynamic way, depending on the request. And as characteristics of the cyber-physical system, we assume this deep penetration into real-life processes and social processes. This sort of intended deep presentation was not there with embedded systems. They were embedded, but actually they did what they were programmed, and they didn't increase the level, the grade of penetration into real-life processes. We also assume that the future cyber-physical system from an architectural point of view will be open, so any kind of actor nodes can join or leave the ensemble, and will have adaptation capabilities which actually develop into evolutionary capabilities. And they will exploit a growing level of system intelligence. They will have what we term sysintelligence, and the applications in human social context will be as dominant as the application in industrial context. So this is the new definition, what we introduce. And if you see that they together project ahead a new type of systems, which will have a significant new type of system, which will have a significant feature, namely this penetration into the real-life processes, which can be implemented in multiple ways. For instance, in the agriculture, when, for instance, you can check the humidity, the water content of plants, and organize the automatic watering accordingly. Then, for instance, you can monitor animals in different forms. You can control home devices remotely and in a collective way, but also you can monitor industrial processes with this penetration. You can implement completely different safety features. You can have artificial links to support the people. And for instance, to implement a comprehensive support for people who need it. And then, just technically, let me ask, is it an embedded system? Is it an embedded system? Of course, the answer is no. This is much more. This is where the cyber physical system can do extras for us in comparison with embedded systems. So this is, if we apply these sort of characteristics in our design exercises, then we can have new implementations of cyber physical systems, which are actually proactive, not just reactive, like self-driving cars or a medical cyber physical system, or home care robotics, or, for instance, rehabilitation equipment. We will talk about these later, and they will show up in my presentation. So cyber physical systems can be utilized in mobility field, military field, transportation field, and obviously the application fields are numerous, and sometimes I say that it is just limited by our fantasy. And what I have seen in the last couple of years, that the social and personal applications are proliferating much faster than, for instance, the industrial application. Please consider what I said, that in the industry 4.0, the traditional definition of cyber-physical systems were considered. When the people realized that with the intelligence revolution, the cyber-physical systems are also becoming more intellectualized, they immediately started to talk about the use of intellectualized system in the field of manufacturing or production. But the people who did innovative research in social and personal application, like my PhD students did, they immediately saw the application opportunities for smart cyber-physical systems and also the business opportunities for this. So as I said before, only our imagination and or negligence is the reason if we cannot find proper application fields for social and personal application. And if we consider these sort of cyber-physical systems as anticipating multi-actor connected systems, then we can achieve different levels of intellectual capabilities and different levels of services and experiences. So let's continue our discussion with the discussion of some other aspects of cyber-physical systems, for instance, those sort of things which are above any type of implementation. And the first term, what we have to little bit elaborate on is system correctness. The system correctness is a very multifaceted thing because it means logical correctness, it means functional correctness, it means temporal correctness, operational correctness, behavioral correctness, and interaction correctness. So the cyber-physical system, if it is correct logically, then it has to safeguard the achievement of the goals on its own. It should be correct functionality from functional perspective, and it has to be equipped with the proper algorithms and computational mechanisms in order to achieve that functionality. Temporal is about timing, and it is very crucial, for instance, internet-based systems, if they can reduce the processing time or the communication can happen in the right time or in the needed time window. Operational correctness is if the hardware, software, and cyberware work in synergy. You may don't feel the problem here, but if you consider that those sort of systems, what we are talking about, are adaptive and evolving, then when the hardware is changed, the software should be changed, or vice versa. When the software is changed, maybe it needs different hardware or different cyberware. So this is what the operational correctness means here. Behavioral correctness, obviously, that important thing because the systems are working in dynamic environment, and depending on the changes in the environment, they have to be able to maintain the expected results and their objectives. And interaction is important also important because it is related to the stakeholders or to the system, and a cyber-physical system has quite large number of stakeholders, and they have to provide the services and the experiences according to the harmonized interest of all the stakeholders. So the other thing is the dependability of cyber-physical system, which is a general overall term. So when we can depend on a cyber-physical system implementation, and there are four aspects of it: the availability, the reliability, the safety, and the maintainability. So actually, these are together which are expected from every cyber-physical system. So fulfillment of these expectations is a kind of meta-level requirement for every cyber-physical system development. If the availability cannot be guaranteed full-time, full operation time availability, if the operational reliability cannot be guaranteed, if the safety is not guaranteed and the maintainability is not guaranteed, in that case, there must be some problem with the problem. Obviously, what is important here to see that at this very moment, all of these receive attention in research and in implementation: availability, reliability, safety, and maintainability. But they together, as the general theory or the general methodology of providing dependability was not addressed yet, according to my best knowledge. And then coming to the end of this block, I would like to suggest you to study that particular paper which I wrote with one of my colleagues about the cyber-physical systems, and the concept, technologies, and implementation principles are summarized there. Then I also recommend you to read the paper, The Cloud-Based Cyber-Physical Systems. This is important because many design challenges and security needs are discussed. Another paper from me, which in a kind of comprehensive way discusses that what the design theory of socialized cyber-physical systems must describe, explain, and predict. And the next one is Mueller's paper on the rise of intelligent cyber-physical systems. So this concludes this block. I come back to the, I stop sharing and come back to the overall screens. How shall we go? I would be very pleased if in the coming or the remaining couple of minutes, we could exchange a couple of questions or answers. Would it be possible, please? Hello?
Yeah, Professor, I could not hear you last. Yes.
So I don't know if anybody has any comment, because actually
there was a question in the chat box. Swati, are you there?
So do you have any comment? This was what you expected. Are you pleased with it, or are you disappointed with it, or what is the opinion?
Yeah, participants, can you give a feedback on this? And Professor Imre, there was a question.
Yes, please.
Yeah.
Pose the question.
What is the difference between IoT and CPS?
Sorry, what is the difference
between IoT and CPS?
Oh, later on I will obviously elaborate on it. The IoT is seen to be a part of a cyber-physical system. IoT is a infrastructural element, and next time when I will talk about the different approaches of distributed computing, you will see that actually it is supporting the implementation of the edge computing mainly. So summarizing the most important thing, IoT is an infrastructural component, or can be an infrastructural component of industrial cyber-physical systems. It is mainly focusing on converting things into active information technology point of view, active units. And obviously, the main focus is a kind of shared information processing between the edge devices.
Dr. Sahu, Dr. Sahu, there is a,
Yes, sir.
yeah, you can.
Hello, sir.
Good afternoon.
Sir, I need to know what are the basics or fundamentals I should know to start working on cyber physical system, and which areas that are relevant to manufacturing domain. Because my background is from mechanical engineering. I don't have any knowledge on IoT or digital twin. So that's why I'm asking what I should know to start working in CPS relevant to manufacturing field.
Right. I cannot see your image. Maybe if you switch your camera on, it will be better. If you have a camera, please switch it on. So
Sahu, can you turn on your video? Yeah. Okay.
excellent. Yeah,
Yes,
thank you
sir.
so much.
Yes, sir.
So I understand your question. So you are focusing on the field of manufacturing and production. And is it not completely clear for me or for you what the relationship between cyber physical systems and automated production can be? If I understood your question correctly.
Yes, sir. Yes, sir. You're right.
So the issue is that obviously we have already a category of cyber physical systems which are abbreviated as CPS, cyber physical production systems. But as I told you, they reflect the traditional interpretation of the cyber physical systems. They also, the recent papers in the last 2-3 years, they also try to consider the adaptability and also, for instance, the evolution related to that. But as far as I know, in the current world of automation, of industrial production processes, the major computational issue is the digital transformation. How can we include more computational elements like sensors and actuators, and how can we reduce the control and supervisory task of the human being? So when we consider cyber physical systems, which do have sensor management capabilities, actually they typically equipped with sensor networks, and they also have opportunities for reasoning and learning-based manipulation of effectors. This can contribute to the automation process. Please see that everybody is talking about Industry 4.0. everybody is talking about cyber-physical systems. But I believe that this sort of digital transformation of the industry is not uniformly distributed. The large international companies who can do research for their own sake and who have uh, economic resources to invest in the digital transformation, because it needs a lot of research, it needs a lot of investment, they can go further and they achieve progress with the digitalization and the informatization of their processes. But the problem is with the medium size and the small scale companies, because obviously they contribute to the automated large-scale processes, but not always has the capacity to do research for their purposes and to invest in the equipment which are needed for the full integration into the supply chains and the production network. So this is what I can tell about the current situation. We are in a development stage. We are just progressing. So I don't believe that there is anything like the exhaustion of cyber-physical systems in the field of production engineering. Just on the contrary, the large-scale useful implementations and utilizations, I should say exploitations, are starting now in our time. So that's why you have to know more about the cyber-physical system. If the concept is clear, if the paradigm is clear, you yourself can study what you can do in a particular context. There are no universal solutions here. Every problem is different. I don't know if I could give you a kind of reasonable answer to your question. Thank you anyway for the question. That was very good.
Sir, one more question, sir. One more question, please.
Go ahead, please.
AI and machine learning under the physical
The sound
artificial intelligence and machine learning. Hello.
Sorry? Yes,
Yeah,
please.
can you repeat the question? So,
Sir, artificial intelligence and machine learning, they come under the domain of cyber physical system, or they are separate from the CPS system?
No, excellent question. Most probably you have seen that the second week we will talk about the relationship of AI techniques and cyber physical systems. You have to see it from the following perspective. If intellectualization of cyber physical system is a challenge, a problem on our table, then when we have to see what artificial intelligence can offer for this purpose. And for the reason that artificial intelligence exists almost 50 years. And it is mainly about extending the human cognitive, intellectual capabilities in the cognitive domain. What is needed for cyber physical systems? We do need the various approaches of artificial intelligence. What I will emphasize in my follow-up presentations, that however, we are not in the position to identify one approach of AI. We always have to make a decision according to what the objective of the cyber physical system development is. Because in itself, artificial intelligence is not a solution for everything. It can be a solution for specific things.
Thank you, sir. Thank you very
Yes.
much.
Thank you very much. So now I see the chat. It is a pity that when I lecturing, I couldn't see, for some reasons. We have to figure out why it is like this. But when I'm lecturing, I cannot see the chat and I cannot see who are participating. So someone asked me that what are the challenges we face by implementation of cyber physical systems. Let me briefly answer. The major challenge is complexity, heterogeneity, and integration. These are the three major things. Cyber physical systems are complex, heterogeneous, and needs careful integration. The other question, what I see here now, is that is the concept of cyber security necessary to implement a kind of cyber physical system? So cyber physical system is considers, for instance, physical part as well. So the physical security is as important as the cyber security part. So my feeling is that contrary to the fact that cybersecurity received more attention in research and development recently, and many people believe that those sort of security issues, what we have developed for conventional physical systems, are sufficient. I believe that the security, as I mentioned, not cyber security or not physical security, but the things together. That's how I see it, and that's why it is complex. Anything else, please, to ask me?
Anyone, any question or comment? There's some, Professor Imre, there's some
Yes.
Comments written in the chat box.
Yeah, this is what
Yeah,
I
he is going
answered
through
now.
them.
I responded. I had to
And I just
apologize.
wanted to ask, like, everybody has been answered, like, one chat has been written by Swati earlier.
Yeah, it has been answered. It has been
Okay,
answered.
so probably I missed it here.
Yeah.
Any other question anybody has? Am I audible to all of you or not?
Yes, sir, yes, audible.
Yes, sir. Yes, sir.
Okay. So, any question? And if there is no question, then we can take a break, and we'll meet at the stipulated time at 4:30 p.m. And I'll take some examples of CPS. I'll take that class and show you how exactly different types of CPS are. We'll try to build a platform, and through this interactive mode, we'll try to give you some hands-on experience also. Okay.
Thank you so much. And
thank you, Professor Imre.
it is my task to thank you all for the attention to this lecture. And tomorrow at 10:30 according to my time and 2 o'clock according to your time, we will continue with the next blocks because we have plenty of blocks to discuss.
Correct.
I would be pleased if we can resolve this particular issue, that if I am presenting my lecture, then why I cannot see the chat and why I cannot see the faces of the people. I will figure out, I will see what the settings are, and then if I manage them tomorrow, maybe it will be better.
We'll also try to talk to some of the experts, our IT professionals in the university and try to
Yeah.
find out what can be a common cause. And I'll drop, if I get some good answer, I'll drop you a mail.
Yeah, thank you so much. Because you remember that when we tried out last week, everything was working perfect.
Yes.
But at that time, I used a different computer, not this one.
Yes.
So, nevertheless, I believe the lecture. Have you managed to record the lecture material?
Yes. It is recorded also. You can see on the top left-hand side of your screen, there is live recording and live on YouTube. It's live on YouTube also.
Excellent. Very good. So tomorrow morning we will continue with the next blocks, and we will process all the blocks what we have here in the lecture.
Yes.
Thank you so much, and have a useful afternoon. Bye for now.
Bye.
See you tomorrow morning. Bye.
Thank you, Emre.
Thank you.
I'll just pause the recording for some time, and we'll meet again at 4:30. Imre, if you want to leave, you can leave. If you want to continue, that's your choice. But I'll be pausing the recording for approximately 17 minutes.
Yes.
Just why I'm saying this, just remind me, because normally when I start delivering my lecture, I forget to start the recording. So just remind me that I have to start recording also.
Yes. Thank you so much. So I'm leaving now to have a little rest, and then see you tomorrow. Bye for now.
Bye. Take care. So all of you, don't vanish. We'll start at 4:30, and I'll take some examples of different cyber-physical systems so that you can connect with what theory Professor Imre is teaching. Actually, we had planned it to be very exhaustive hands-on session. But unfortunately, because of COVID, Professor Imre couldn't come, and we know conducting lab from a remote location is very difficult, and you may not have access to all the software and all the tools which we are going to teach. But in our tutorials, in our lectures, which Professor Gupta and I will be taking, will demonstrate you all those things, what theoretical portion Professor Imre is teaching. So that's the idea behind this being a practical topic. That's the idea behind this GIAN course actually. And we must thank the GIAN, IIT Kharagpur, for sponsoring and funding this course, and allowing us to have this course in an online manner also, and so that we can listen to Professor Imre. Thank you. How can we stop, or shall I relink? How can we pause on? Is there any idea how can we pause on the YouTube?
Which one?
Or to pause on YouTube?
No, we have to
I think I have to stop and then start again. No?
stop and again start actually. That is the only way.
Probably not, because in between there were power fluctuation. You have become the host, so you have to stop it actually. I'm not able to see those three buttons.
Yeah, I will make you host actually, because it everything is at your end actually.
Yeah,